Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating paper from DeepSeek on inference-time scaling for generalist reward modeling. It's got some really interesting implications for how we build more capable AI.
Yeah, I saw that one. Pretty impressive stuff. They're basically trying to create a single reward model that can handle a wide range of tasks, right? Instead of training separate reward models for each specific thing.
That's the idea, but I'm always a little skeptical of these generalist approaches. It sounds great in theory, but does it really translate to better performance in practice? Or are we just creating a jack of all trades, master of none?
I think it's a worthy goal. The brain is a pretty generalist system in a way. We can learn to do all sorts of things. The question is, how do we get AI to achieve that same level of flexibility? This idea of scaling inference time seems interesting. Could be less brute force.
Well, let's break it down a bit. The core concept here is that they're using a single large language model to predict rewards for different actions across a variety of tasks. And the key innovation is how they scale the inference process, so they are not retraining for each new task. Otto, maybe you can elaborate on the technical details.
Sure. So, the traditional approach is to train a separate reward model for each task, but that's obviously inefficient, especially as you want to handle more and more different goals. What DeepSeek is doing is training one huge model on a diverse data set of tasks, and then, at inference time, they use techniques like prompt engineering and in-context learning to guide the model to produce accurate reward predictions for new tasks it hasn't seen before. It's pretty clever.
Okay, so it's basically relying on the pre-trained model's ability to generalize from its training data. Isn't that just hoping the model has learned the right abstractions?
To some extent, yes. But they're also using prompting to provide the model with additional information about the specific task at hand. So it's not just blindly generalizing, it's using contextual information to make more informed predictions. Like, imagine you want the model to predict the reward for a robot picking up a cup. You would give it a prompt that describes the task, the current state of the robot and the environment, and the action the robot is taking. And then the model predicts how good that action is in that context.
Right, so it's like giving the model a little nudge in the right direction. But I wonder, how sensitive is this to the specific phrasing of the prompt? If you phrase it slightly differently, do you get wildly different reward predictions?
That's a great question, Donald. And it's something they actually address in the paper. They found that prompt engineering is crucial, but they also developed techniques to make the model more robust to variations in prompt phrasing. I think it's about making the rewards functions learn the concepts rather than the syntax, so to speak.
I'm still not convinced that this is a truly general solution. It feels like we're just shifting the complexity from training individual models to designing clever prompts. And who designs those prompts? Humans. Isn't that still a bottleneck?
Well, yes, prompt engineering can be challenging. But there's also research into automatically generating prompts. And even if humans are involved, it's still more efficient than training a whole new model for every task. Plus, this approach allows for zero-shot learning, which is a huge advantage. The model can, in theory, generalize to tasks it has never seen before.
The zero-shot learning aspect is definitely interesting. It hints at some underlying understanding, or at least a strong ability to extrapolate. But I'm still concerned about the representation of the task itself. Is it just a string of text, or is there some internal representation that captures the spatiotemporal relationships within the task?
That's where the scaling part comes in, I think. They found that larger models perform significantly better at this task. Presumably, the larger models have a better capacity to represent these complex relationships, even if it's not explicitly encoded.
Exactly. It's that emergent behavior we see with large language models. They're not explicitly programmed to understand spatiotemporal relationships, but they seem to learn them implicitly from the data. It's kind of mind-blowing, actually.
Emergent behavior or overfitting. It's hard to tell the difference sometimes. Just because a model performs well on a set of benchmark tasks doesn't mean it truly understands the underlying principles. I mean, we've seen examples of AI systems that excel at games but completely fail in the real world because they've learned to exploit loopholes in the game's rules.
That's a valid point. It's all about how the model is grounding its knowledge. Is it just learning statistical correlations, or is it actually building a model of the world? I suspect it's mostly the former, at least with current deep learning approaches.
Okay, so let's say we accept that there might be limitations with this approach. What are the potential benefits? Where could this be applied in the real world?
Robotics is an obvious one. Imagine you have a robot that needs to perform a variety of tasks in a dynamic environment. Instead of training separate reward functions for each task, you could use a generalist reward model to guide the robot's actions. It could adapt to new situations and learn new skills much more quickly.
Yeah, but what about safety? If the reward model is not perfectly accurate, the robot could end up doing something dangerous. We've already seen examples of robots causing harm because of faulty programming. A generalist model might amplify those risks.
That's a critical concern. Safety has to be paramount, especially when we're talking about robots interacting with the physical world. Perhaps we need to incorporate some kind of safety constraints into the reward function itself, or maybe use a separate safety model to monitor the robot's actions.
There's also potential in areas like personalized medicine. A generalist reward model could be used to predict the best treatment plan for a patient based on their individual characteristics and medical history. It could take into account a wide range of factors and identify subtle patterns that a human doctor might miss.
That's a really interesting application. It's like having a virtual medical expert that can analyze vast amounts of data and provide personalized recommendations. But again, we have to be careful about bias. If the training data is biased, the reward model could end up perpetuating those biases in its recommendations.
And who's responsible if the model makes a mistake? A doctor can be held liable for malpractice, but what about an AI system? These are ethical and legal questions that we need to address before we start deploying these systems in critical areas like healthcare.
Absolutely. Accountability is key. We need to have clear lines of responsibility and mechanisms for auditing the model's decisions. And we need to ensure that the model is transparent and explainable so that humans can understand why it's making certain recommendations.
So it sounds like there's a lot of potential here, but also a lot of challenges. What are some of the key research directions that could help us overcome these challenges?
I think we need to focus on improving the robustness and generalization capabilities of these models. One approach could be to incorporate more structured knowledge into the model, maybe through neuro-symbolic techniques. Another could be to develop better methods for prompt engineering and in-context learning. And of course, we need to keep scaling up the models and see where that takes us.
I agree that neuro-symbolic integration is crucial. We need to move beyond purely data-driven approaches and incorporate more explicit representations of knowledge and reasoning. We also need to develop better methods for verifying and validating these models to ensure that they're not just memorizing patterns, but actually understanding the underlying principles.
From my perspective, I think we need to focus on the spatiotemporal aspects of intelligence. How can we design models that can reason about time and space in a more sophisticated way? How can we represent different coordinate systems and translate between them? I suspect that this is a key missing piece in the puzzle.
Building on that, and connecting to my own work, I think the reversal curse highlights the need for better representation learning. If we can develop models that can learn more nuanced and multi-layered representations, we might be able to overcome some of the limitations of current transformer architectures. And I'm particularly interested in exploring how we can draw inspiration from the brain's modularity and hierarchical processing to design more biologically plausible AI systems. And this extends to reward learning. How are the reward functions built in the brain? What mechanisms are used to change these reward functions?
Yeah, I think understanding how the brain handles reward learning is definitely a promising avenue. I'm also curious about how these generalist reward models could be used to create more autonomous agents. If we can train an agent to learn a wide range of tasks, it could potentially explore and learn on its own without requiring constant human supervision.
That sounds like a recipe for disaster. I think we need to be very careful about giving AI systems too much autonomy. We need to make sure that they're aligned with our values and that they're not going to do anything that could harm us or the environment. Neuro-symbolic may help here, more constraints and rules, not just emergent behavior.
Well, alignment is definitely a crucial issue, but I think autonomy is also essential for true intelligence. We need to find a way to balance these two competing goals. And I think a key part of that is developing better methods for explaining AI decisions. If we can understand why an AI system is making a certain decision, we can be more confident that it's aligned with our values.
It's a fascinating and complex field, with a lot of exciting research happening. The DeepSeek paper is just one small piece of the puzzle, but it highlights the potential of generalist reward modeling and the importance of scaling inference time. Thanks for joining me today for this discussion.